Okay, so once again, your first homework will be posted sometime tomorrow afternoon. I don't know exactly when, but when it's posted, I'll send an announcement out and tell you where to find it and how to do it. And it'll be due next Friday night, right? So there's no quiz on this Saturday. The first quiz will be next Saturday, right? So it's basically based on, the homework will basically be on what we did on Tuesday and what we're doing today, right? We're going to finish up what we're doing today. Okay, so did everyone get into Canvas, by the way? Okay, good. Okay, so what we need to do is finish up this PowerPoint, and actually we've got to start the next PowerPoint, but we're not going to get that far in the next PowerPoint today. Basically going to finish, spend most of the time finishing this PowerPoint that we started on Tuesday. So let's go to the next thing that we did. So we started with proportions, and we'll do some more examples with, we'll do examples in the notes with proportions in a bit, but then we just do a couple more slides here before we do examples in the notes. So we did examples on Tuesday of basically just one sort of variable, like 4 divided by x cubed, and 1/3 times x squared, things like that. But you can actually do more complicated proportions, and these also come up in physics from time to time too, where you have more complicated situations where some quantity, say z, is depends on both x and y. So it depends on 2 variables, not just one variable. So the question is, how do you figure out how proportions work for these sort of more complicated cases where you have 2 variables that depend on z? Okay, so first of all, the new thing that I did here is I put c. So c can be any number. Remember what we did on Tuesday? We had 4 times x cubed, but the 4 doesn't matter. It can be anything. We had 1/3 x squared, but the 1/3 doesn't matter. You ignore the numbers when you're doing proportions. So I'm doing it more generally and saying c is some number where it can be anything you want it to be. It could be 100, 1,000,000. It doesn't matter because c doesn't matter when you're doing proportions. The number doesn't matter, so I'm just writing it as c. Okay, so besides that, suppose you have this equation here, right? C times x cubed y squared. So the question is, how do you figure out how z changes, for instance, proportionally speaking, if you change x or y by some factor, or x and y by some factor? So to understand this, what you got to do is you got to basically do it one step at a time. What I mean by that is you got to figure out, well, if you change x by some factor, what happens to z? And then you have to figure out, well, if you change y by some factor, what happens to z? So let's do an example here, right? So suppose we increase x by 2, right? So basically what we want to do is figure out first, suppose we just changed x by 2, which means we double x, we take x, we multiply it by 2, right? Remember, factors are always multiplication or division. So if you take x, multiply it by 2, what happens to z? Okay, so first of all, none of these things are in a denominator. It's not x cubed divided by y squared or y squared divided. Oops, I almost hit my computer here. Or it's not y squared divided by x cubed, right? It's just x cubed times y squared, right? So both of these things are proportional to z. In other words, if x or y goes up, then z goes up. If x or y goes down, then z goes down. But you could also pay attention to the exponents, right? So it's x cubed. So if x goes up by 2, z goes up, but it doesn't go up by 2. It goes up by 2 cubed because it's x cubed. It's not x. So 2 cubed is 8. So if all you do is change x, you increase it by 2, and then that would increase whatever z was by a factor of 8, meaning you take z and you multiply it by 8 because factors are multiplication or division. And then suppose you took y and increased it by 4. So then you took y and you increased it by 4, and you want to figure out what happens to z. Once again, z and y are proportional. Nothing's in the denominator here. So basically, if you make y bigger, then z gets bigger. But it doesn't just get bigger by 4. It gets bigger by 4 squared because it's y squared, right? So 4 squared is 16. So if you changed, increased y by a factor of 4, then z would go up by 16, which is 4 squared. If you did both of them, if you increased x by 2 and you increased y by 4, one of them makes it go up by 8, the other one makes it go up by 16. So anything that makes it go up is like multiplication. So the 2 factors together would be like multiplying the factors from each contribution together, right? So one makes it go up by 8, one makes it go up by 16. So the overall change would be 8 times 16, which is whatever it is, 128, right? Does everyone get that? Okay, let's do another example with the same equation here. So suppose you increase x by 3. Once again, x and z are proportional. So if you increase x by 3, then z goes up. But it doesn't go up by 3. What does it go up by? It goes up, well, you can read it, but it goes up by 3 squared, right? So 3 squared is 9. So if the only thing you did is change x by, if the only thing you did is increase x by a factor of 3, that would increase z by 9 by itself. Okay, so then what if you took y and you decreased it, right? So that's the important thing to read. Decreased by a factor of 2, or basically halved it, is the same thing. So if you decrease y, z and y are proportional, so z would also decrease, but it doesn't just decrease by 2. It would decrease by 2 squared, because it's y squared. So 2 squared is 4. So anytime you have a decrease, it's like dividing, or something in the denominator. So the fact that x increases z by 27, and y would decrease z by 16, hold on one second. Y would decrease z by 16 gives you an overall factor change of 27, because it's increasing, divided by 16, because it's decreasing. And 27 over 4. I meant to say 4. 2 squared is 4. I thought it was 4. I thought we were decreasing y by 4, but it's 2, right? So 2 squared is 4. So anyhow, it'd be an increase of 27 from x and a decrease of 4 from y, so you get 27 divided by 4, which is 6.25, right? Okay.
That's dependent that you multiply x before you cube it. If it was like x cubed multiplied by 2, it would be a different value? You know what I'm saying?
No, repeat that one again. So we're increasing x by 3, right?
Uh-huh. So instead of 2, now it's x. Let's just say hypothetically. If x was 2.
Yeah, if x was 2, then it'd be 2 cubed. It's a separate problem. These two bullet points are two separate things, right?
Yeah.
So the first case, we increased x by 2, right? And that was 2 cubed, which is 8. It would increase. Changing x alone would increase it by 8, right?
Okay.
But in this example, we're increasing it by 3, not 2.
No, yeah, I understand.
Okay, so what are you saying?
I'm saying that's dependent that you multiply x by 3 before you cube it. Like it's x cubed.
Yeah.
Yeah, otherwise, how would you do that? It was like x cubed 10 times 2. Because you wouldn't know.
If it, sorry, come one more time. If it was x cubed times what?
If it was x cubed, then increased by a factor of 3. So x cubed is in.
Oh, no. Just x increases by 3, not x cubed. Is that what you're saying?
Yeah, that's what
No. Just x, not x cubed.
Okay.
All we're doing is increasing x.
Okay.
Okay? All right. Any other questions? Yeah.
Does it matter about the wording? So if x was decreased and then y was increased?
Yeah. No, the increasing and decreasing.
But does it matter which order they come in? Or can you just
Which one do you do first? So if you did y first and then x, is that what you're saying? No.
we assume that if it's one's being increased and one's being decreased, then they end up being divided times y?
No. So the fact that x is increasing or decreasing, or y is increasing or decreasing, determines what happens to z, correct? And then once you figure out what each thing does to z, if whatever increases z, that goes in the numerator. And if something decreases z, that goes in the denominator, right? Okay, so we'll do another example on the next slide. Maybe it's a little bit clearer. So now we have another equation. It's x squared divided by y to the 4th. So we want to change x and y somehow. So the first thing you have to notice is that there's a y in the denominator, and the x squared is not in the denominator, it's in the numerator. So x is proportional to z. In other words, if you make x bigger, z gets bigger. If you make x smaller, z gets smaller. But once again, it depends on the factor squared because it's x squared. But the y is in the denominator, right? Which means that they're opposite of one another. If you make y smaller, z gets bigger. If you make y bigger, z gets smaller. But it's not just the factor, it's the factor to the 4th because it's y to the 4th, right? There's a 4 there. So that's how we're going to approach this problem and see how it works out. So suppose we took x and increased it by a factor of 3. Once again, because x is in the numerator, if we make x bigger, then z gets bigger. But it doesn't get bigger by just 3. It gets bigger by 3 squared because it's x squared. So 3 squared is 9. So if all you did was just change, increase x by 3, then z would increase by 9, right? Now, if you also increase y by 2, y's in the bottom. So if y gets bigger, z gets smaller, right? So, but it's not just 2. It doesn't just decrease by 2. It decreases by 2 to the 4th, right, which is 16. So increasing y by 2 would decrease z by 16, correct? So once again, any increase goes in the numerator, any decrease goes in the denominator. So you get an increase of 9 from x, and then a decrease of 16 from y, and you get 9 divided by 16 is the overall change. So you can multiply whatever z was by 9 over 16, or you can convert it to a fraction, which is 0.56, and just multiply z by 0.56. If we get smaller, it's almost half as much as it used to be, right? Does that make sense? And let's do another one. Then we'll do more in the notes, too. There's some more examples in the notes. Okay, so suppose it's the same thing, but this time we're decreasing x first by 4. So once again, x and z are proportional, meaning that if you decrease x, z goes down as well. But it doesn't just go down by 4, it goes down by 4 squared. So 4 squared is 16. So just decreasing x by 4 decreases z by 16 by itself. Then suppose we decreased y by a factor of 3. So we're decreasing both, but we're also decreasing y by a factor of 3. So y, is in the denominator, so we went over this. If y gets smaller, then z gets bigger. But it doesn't get bigger by 3, it gets bigger by 3 to the 4th, which is 81. It's 9 times 9. So, decreasing x decreases z by 16. Decreasing y increases z by 81. So any increase goes in the numerator, any decrease goes in the denominator. And it's 81 divided by 16, which is 5. It's a little bit more than 5, right? 5.06. So, that's how z would change. It would change by a factor of 5.06, right? Does that make sense? Okay, so let's do some examples in the notes and see if you get it. The first couple examples are kind of straightforward. The last one's a little bit more complicated. So we'll see. Hopefully you get most of it. All right, I got to turn this computer on because I almost knocked it over before. Okay. Let's see, it'll disappear. Okay, so let's do some of these examples here. I'm going to type these examples. This is one of the few cases I can type everything, and my handwriting doesn't get in the way. All right, so the setup of this is slightly different than how I showed you do in the notes, but you'll see how we do it. All right, where c is some number, right? So that number could be anything. It could be 5, 10, 15, 20, negative, whatever, doesn't matter. And so we're setting it up a little bit differently. So for some value, this is the whole point of proportions, by the way. So for some value of c and x, y is equal to 2. So that's given, right? So the whole point of proportions is you need to know what c or x is. All you need to know is what the initial value of y is. And then what you want to do is change x or something and see how y changes. So for instance, c could be 2 and x could be 1, right? That's one way you can get 2. But it doesn't have to be that. It can be any combination of c and x that give you 2. It doesn't matter. But that's the initial given information. This is the value that we're starting from. Y is equal to 2. Okay, so that's the given. Now let's ask a question. So the question is, what's the new value of y if x is doubled? So double means increasing or multiplying all right, I'll fix that later. Factor of 2, right? It's the same thing. You'd say doubling is the same thing as multiplying by 2, right? Or increasing by a factor of 2. All right, that's the question, right? So if you double x, what's the new value of y? That's it, right? So like I said, these first couple are pretty straightforward, but let's see if you can figure it out. Okay, so the first thing I'm going to do is figure out, is x proportional to y, or is it inversely proportional to y? So the question is, that's the first question, is it inversely proportional or proportional to? proportional. It's not divided by x squared, right? It's just x squared. That means if you make x bigger, if you double it, for instance, then y gets bigger, right? They do the same thing. But it's not just, it just doesn't double. Why doesn't it double? Because it's x squared, right? Okay, so increasing x increases y, but x increases by a factor of 2. I'm going to do it with a caret because it automatically calculates it. But that's 2 squared, right? A caret means 2 squared, right? So it would increase it by a factor of 4, right? Does everyone, I mean, everyone gets that, right? So the new value of y is, and I'm just going to type it because I can type it. All right, so this is some new notation. I do this quite often in the class, even when I do physics. If I have a variable that's just changing, it changes from one thing to another, I use this notation to represent this new thing. So it's a y, it's technically called prime. I say y prime all the time. It's just a y in a single quotation, but it's y prime, that's what we say. It's basically y, but it's the new value of y, right? So the new value of y, which I call y prime, is the old value of y, which was 2, right, times how much it changes by, because when, well, increasing is multiplication, right? So because it's increasing, we multiply. So it's 2 times 4, which is 8, right? So that's the new value of y, right? It would go from 2 to 8. You don't need to know what c and x are initially. All you need to know is what, what happens to x, how that affects y, right? All right, so does that make sense? Hopefully it does. It's not super hard. I need to get rid of that. Okay, so we're going to do another example using the same equation here. All right, so the next part is, all right, so using the original given information. So in other words, supposing y starts at 2 again, so we're not compounding from part A. It's not 8. No, it's just back to 2. So if x is reduced by a factor of 3, what's the new value of y? All right, I'm going to copy this. I'm going to change the wording here, but it's pretty similar wording. So, okay, so first of all, if I reduce x, what happens to y? Does it also get reduced or does it go up? It gets reduced, right? It's the proportional. So, like I said, I'm going to change this. So here we're decreasing x, right? So decreasing x decreases y, right? But x decreases by a factor of, okay, so how much would x decrease by if the factor is 3? Yeah, it's 3 squared, right? Because it's x squared, right? X squared, right? So it's 3 squared, which is 9, right? So what would the new value of y be? Yeah, so the new value, which is y prime, is 2, because we're assuming it's the original value of y, divided by, because anything that's decreasing is dividing, right? That's what we mean. So it's 2/9 or 0.22, right? So that would be the new value of y. All right, does that make sense? So like I said, the first couple examples are pretty straightforward, hopefully. But then we'll go on to a harder one. Let me see how you do that one with that one. All right, so does that make sense so far? All right, so then, okay, so suppose y is equal to c divided by x cubed. Once again, where c is some number. Okay, so for some value of c and x, y is equal to 10 for this case. That's just the initial value of y, right? Okay, so the question is this. If x is halved, you can do this too, right? So x is reducing or decreasing by a factor of 2, that's the same thing as having, what's the new value of y? Okay, so the first thing you have to do is you have to figure out, is z and x proportional, or x cubed, whatever. So x is in the denominator, right? So if I make x smaller by reducing it by 2, what happens to y? Does it decrease or does it increase? It increases, right? Because it's in the denominator. So I'm going to obviously change what's going on here, right? But it's pretty similar wording, so I'm just going to borrow that and change what I need to. Okay, so decreasing x, which is what we're doing here, increases y, right? Because they're inversely proportional. But x increases, so how much does x increase by for this case here? So it's not just 2, right? So we're having it, right? Decreasing it by 2, but it doesn't increase by 2. What does it increase by? 2 cubed, right? Which is 8, right? So it would go up by 8. So what would the new value of y be? Yeah. So the new value of y is the old value of y, which was 10, or the initial value of y, times how much it goes up by, which is 8, right? So that's the new value of y.
If you're having it, wouldn't it be 0.5 instead of 2?
Yeah, so this is the thing. So I pointed this out on the PowerPoint on Tuesday. So having, right? So multiplying by a fraction is the same thing as dividing by the whole number, right?
Yeah.
Okay, so there's two ways of looking at the same thing. That makes sense? Okay. All right, so does anyone have any other questions on that? We're good? I'm going to borrow part of this too because it's pretty similar to the next. Okay, so the next part, same, oh, that got messed up. All right, maybe I can't do that. All right, so if x is, all right, let's see. I got to change this a little bit. So using the original information, so in other words, y is 10. It's not 80, right? We're back to 10. If x is increased by a factor of 3, which is the same thing as saying it's tripling x, right? You can say x is tripled or increased by a factor of 3. Then what's the new value of y, right? Okay, so once again, right, if you make x bigger, right, because we're increasing it by 3, we're tripling it, what happens to y? Does it go up or go down? It goes down, right, because they're inverse. But what does it go down by? Yeah, it goes down by 3 cubed, right? All right, so this is opposite, right? So basically, this what we're doing is increasing x decreases y because they're inversely related. But x, it's supposed to be decreases. I'll change that in a second. But x decreases by a factor of, so what's the factor again? One more time. 3 cubed, right? Which is 27, right? So decrease by 27. So decreasing, of course, means you divide, right? So what would the new value of y be? Yeah, right. So it's actually 10 over 27. That's the best way to write it. But as a decimal, it's 0.3704. All right, so does that make sense so far? All right, those are kind of straightforward, right? Let's do a more complicated one. All right, suppose z, so this is one with, depends on two things. It's c times x squared divided by, oops, I did that. Okay, divided by y squared, where c is once again some number. Doesn't matter what that is. Okay, so for this case, for some value of x, y, and z, z is 20 or equals 20, doesn't matter. All right, so z is 20, that's what we're starting from. And we're going to change x and y and see what happens. So if x is increased by a factor of 3 and y is decreased by a factor of 3, so it's the same factor, but one is increasing, one is decreasing. What is the new value of z? All right, so the best way to do these is basically one at a time. So in other words, just focus on x, right? So is x proportional to z? In other words, if x gets bigger, does z get bigger? Yeah, because it's not in the denominator. So if we take x and increase it by 3, then z increases, right? So if x is increased by a factor of 3, then z increases by a factor of, so what would the factor be though? It's not just 3, right? It's 3 squared because it's x squared, right? All right, so everyone gets that part so far? Now you got to look at y. So y is in the denominator, right? So basically if we decrease y, what happens to z? It increases, right? So if y is decreased by, what is it, 3? Then z increases, because they're opposite, right? They're inverse, by a factor of, what is it again, for 3 squared? They're both squared, right? So 3 squared is 9. So what we're saying here is increasing x by 3 increases z by 9. Also decreasing y by 3 also increases z by 9. So the overall factor is 9 times 9 because they're both increases, right? And increases are multiplication. So it would be 81 times bigger than it originally was, right? That's the overall factor. Thus, the new value of z is, all right, so what would the new value of z be, do you think? Right. So it's 20, the original value, times 81, which is 1620, right? All right, does that make sense so far? Okay. Let's do one more part. Okay, so I'll just type it out again. It doesn't matter. Okay, so using the original given information. So in other words, z is not 1620. Z is 20. It's the original value of z. All right, hold on. All right, so if x is increased by a factor of 2, and y is increased by a factor of 4, what is the new value of z? All right, so once again, we have to do this sort of step by step. Let me just copy this sentence first. All right, so once again, what happens if we increase x? What happens to z? Does it increase or decrease again? It increases, right? But it doesn't increase by 2. It increases by what? 2 squared, right? Because it's x squared. So it increases by 4. All right, that makes sense? Okay. Now, what happens to, what does y do to z? Where's the equation? Okay, so here it is. So we're increasing y as well. Both of them increase, right? But if we increase y, what happens to z? Does it go up or down? It decreases, but it doesn't just decrease by 2, or sorry, by 4. It doesn't decrease by 4. What does it decrease by? 4 squared, which is 16, right? So if y, I got to change this, obviously. All right. So if y is increased by 4, then z decreases by a factor of 4 squared, which is 16. Okay. So the overall factor is, what do you think the overall factor is? The increase, x increases z by 4. But y decreases z by 16, right? So it's 4 divided by 16, right? Because that's how it works. So it's 0.25, 1/4 basically, right? Okay. So the new value of z is, so basically you take the original value z, which we're assuming is 20, and you multiply it by the factor change, which is 0.025, and of course you get 5. It's the same thing as a quarter, right, of 20, which is 5. Yeah.
In that first sentence, the x is increased by the factor of 3, shouldn't that be
Yes. Sorry. Forget to change it. Yeah, sometimes when I copy things, I forget to change things, so just let me know that. That happens every once in a while. Okay, so does that make sense? All right, so if that makes sense, let me go on to back to the PowerPoint, talk about the next thing. Okay, so we're done with proportions. You'll be on the homework tomorrow. You'll see some more of them. The next thing I want to talk about is something that you probably know how to do, but I'm just showing you how I do it because it's better. Well, I don't know if it's better, but I have a sort of systematic way of doing unit conversions, and unit conversions are sort of important to know. I'm sure you've done them in other classes, and you've probably done them before. But let me just show them my way, and you can do them your way as long as you know how to get the right answer. That's the most important thing. So, of course, you know, in this country we use backwards units. You know, we use feet and miles, and Fahrenheit, and all this stuff that no one else uses. So you need to go, you know, you need to know how to convert between our system and, of course, the metric system. Everything that we do in this class is, of course, it's going to be using the metric system. It's not going to be using the English system. In particular, we're going to use a subset of the metric system, which most sciences use, which is called the MKS system. All that means is that we're going to use meters to represent lengths, which is the M. We're going to use kilograms to represent mass, which we'll see in a bit. And we're going to use seconds to represent units of time, typically. So that's the MKS subsystem in the metric system. Okay, so anyhow, so we need to convert between, you know, one unit and the other unit. So I don't know if you ever thought about it, but basically when you convert units, basically what you want to do is just convert the unit. You don't want to change the measurement. So if this room is 50 feet wide, I don't know what it is, but I'm just saying it's 50 feet wide. You want to convert it to meters. When you do the conversion to meters, you don't want to make it longer or shorter. You want to make it 50 feet, just convert it to meters, right? So you don't want to change the measurement. So what you're doing with the unit conversions is taking the original units and multiplying them by 1 so that you don't change the measurement itself, right? Because if you have some measurement, you multiply it by 1 and 1 again and 1 again and 1 again, it doesn't change anything, right? And these ones just represent basic relationship between different units, right? So I'll show you a pretty straightforward example that everyone, I think, would probably know how to do by themselves. But then we're going to do a more complicated example in the notes, and you'll see how it works with a more complicated example. So suppose you know that 1 inch is 2.54 centimeters. And in case you're wondering if you have to memorize what 1 inch is in centimeters, and then you don't. In fact, most of the units that you'll see on the quizzes and the homeworks are units that I make up, because if they're normal units, you can just Google unit conversions. Google is really good at that now. So I make up my own units that no one's ever heard of, that I haven't heard of until I make them up. So the point is, the basic relationship between the units, like 1 inch is 2.54 centimeters, will be in the question. So you don't have to memorize these things, right? But anyway, suppose you know that 1 inch is 2.54 centimeters. You're given this information, and you want to use it to do a unit conversion. So what you can do, and this is how I approach these unit conversions, which you might have seen or might not have seen, is if you divide both sides of that equation by 1 inch, you get 1 inch divided by 1 inch, which is literally the number 1. It's identical to 1. And then on the right-hand side, you get 2.54 centimeters divided by 1 inch, which is what I wrote here. So the number 1, and whenever you see a number 1, if you wanted to, you could write 2.54 centimeters divided by an inch. That's the same thing as the number 1. If I take the inverse of both sides, if I flip both of them around, well, the inverse of 1 is 1. And then I get this for the inverse of this. So 1 inch divided by 2.54 centimeters is also the number 1. If you wanted to, mess up your friends and, writing down their phone number that has a 1 in it, you can write 1 inch divided by 2.54 centimeters because it's the same thing as the number 1. So what you're doing is using one of these versions of 1 to do the unit conversion. So for instance, if you're trying to convert 5 inches to centimeters, if you multiply a 5 inch by 1, that doesn't change anything, right? Because it's still 5 inches. And then what you do is you use this version of 1 because you have an inch in basically the numerator. You want an inch in the denominator to cancel out the inch, right? Because you want the inches to cancel out. And you get 5 times 2.4, 5 inches times 2.54 centimeters divided by an inch is the same thing as 5 inches. And the inches cancel out, you just get centimeters left over. So it's just 5 times 2.54 centimeters, right? 5 times 2.54 centimeters. And then if you want to do the other way around, and these are pretty straightforward, but if you wanted to go from centimeters to inches, once again, you multiply centimeters by 1. But this time you use this one because you want to get rid of the centimeters. So it's 3 centimeters times 1 inch divided by 2.54 centimeters. The centimeters cancel out. And you get basically 3 divided by 2.54 inches, right? So all you're doing in unit conversions is multiplying by different versions of 1 to get what you want to get. So it makes sense when you do a more complicated example, right? Which is what I'm going to do. Can I do this? No, I can't do that. Which I'm going to do now, right? So that's pretty straightforward. I think most people can do that pretty easily. Maybe some people can do this example easily. But when you see units you've never seen before, trust me, you get a little bit confused on how to do the unit conversion sometimes. So this is sort of a straight step-by-step approach to doing unit conversions. So let me show you how this works. Okay, so let me sit down again. Okay, so these are typical units, though. So suppose that we know that 1 mile, or 1 mile for short, MI is the shorthand notation for mile, is 1.61 kilometers, right? So suppose you know this. Okay, so the question is convert 60 miles per hour to meter per second. Okay, so there's actually one of them you don't really need to do, but it helps to do it anyhow. There's actually 3 unit conversions you need to do. Does anyone see the 3? So first of all, there's a mile here. You want to get it to meters, so there's some unit conversion there. But if you look at what we know, we only know that 1 mile is what it is in relation to a kilometer, not a meter, right? It's not kilometers per second. We want meters per second. So what I'm saying is you have to convert miles to kilometers. Then you have to convert kilometers to meters, right, is what I'm trying to say. And then there's another one. We have to convert hours to seconds, right? So there's 3 unit conversions we need to do, technically, to do this. So what I'm going to do is write down the basic relationships between the units that we needed to use, and then write down different versions of 1. So one of them is this one. 1 mile is 1.61 kilometers. Let's start there. Okay, so from this, so I do this arrow sometimes. It means that from this equation, I can get another equation or something else from this equation. So if I divide both sides by a mile, then I get this version of 1. So I get 1.61 kilometers divided by 1 mile is equal to 1, right? So that's literally the number 1. The number 1 is 1.61 kilometers divided by a mile. Or I can take the inverse of both sides, and I get 1 because the inverse of 1 is 1, but the inverse of this side is 1 mile. Divided by 1.61 kilometers, right? That's another way to write the number 1, correct? So that's one relationship between two of the units that we need to figure out. But we also need to convert kilometers to meters, right? Because in the end we want meters, we don't want kilometers. So what is 1 kilometer in terms of a meter? So what is a kilo? Everyone should know prefixes, right? It's 1,000, right? So from this, you can get two versions of 1, 2. If I divide both sides by 1 kilometer, I get the number 1 is equal to 1,000 meters divided by a kilometer. Or I can take the inverse of both sides, and I get 1 is equal to 1 kilometer divided by 1,000 meters. Right, so that's another version of 1, relating kilometers to meters. And then there's a third one we need to do. That's hours to seconds, right? We need to convert hours to seconds somehow. So this one you just think about. So what is 1 hour in terms of seconds? In other words, how many seconds are in an hour? Yeah, there's 60 minutes in an hour and 60 seconds per minute, right? So that's 60 squared seconds, which is 3,600 seconds. So if I divide both sides by an hour, I get 1. So the number 1, once again, is equal to 3,600 seconds divided by an hour, or you can do the inverse of both of these. So that's another version of 1. So we have all these different versions of 1, and basically we have to use 3 of these versions of 1 to do the unit conversion, right? So now we got to do the conversion. That's the setup to the conversion. We haven't done the conversion yet. Okay, so it's 60 miles an hour. That's what we're trying to convert. So what we want to do is multiply 60 miles per hour by 3 ones to get this conversion, right? So I'm going to do it step by step. So I want to get rid of the miles first, right? Let's just start with the miles, right? I want to get rid of this thing, right? Which is in the numerator, right? Miles in the numerator. So which one of these versions of 1 do I want to use? Do I want to use this one or this one? The first one, because that has miles in the denominator, right? All right. I haven't done anything with the other 2 ones. They're just there. So I'm going to color code it, right? So that cancels that, right? So what do I have now? I have kilometers divided per hour. So kilometers per hour. So if I multiply 60 times 1.61, that gives me the conversion to kilometers per hour. But I don't want kilometers per hour. I want meters per second. So the next thing I want to do is I want to get rid of the kilometers. The kilometers is in the numerator. So which one of these, sorry, hold on. I got to copy something quick. So I'm going to go up, and what I want to do is find which version of the next version of 1 I want to use, right? So the kilometers are in the top. So which one of these do I use? This one or this one? The first one, right? The one with the kilometers in the bottom. All right. Oops, I got to switch back. Okay, so so when I do that, that cancels the kilometers, right? So now what I have 60 times 1.61 times 1,000 meters per hour, right? That converts to meters per hour. Now I want to get rid of the hour in terms of seconds, but the hour's in the denominator. Hold on, I got to copy this. I keep on forgetting. Okay, so the hours is in the denominator. So which version do I use? Do I use this one or that one? Second one, right? This one? All right, I'll just look like that. So, so when I do this, this cancels the hours, right? So the hours go away. And what do I have left? I have meters at the top, seconds at the bottom. So if you look at the whole algebra, it's 60 times 1.61 times 1,000 divided by 3,600, right? That gives you the conversion to meters per second. So if you know how to do it your own way, it's fine. But this is sort of a step-by-step way of doing complicated unit conversions. And then you have meters and seconds left over, and whatever that works out to be. I think it's like 26.83. Yeah, 26.83. Right? So like I said, unit conversions are something you probably saw before, so if you have your own way of doing it that works, it's fine. But this is how I do it. It might help some people in here. Yeah?
I get all the math, but what are you doing with the extra ones and
Oh, I'm just saying that these represent 3 ones that you're going to use for unit conversions. We're multiplying, that's essentially what we're doing, right? We're taking 60 miles per hour, we're multiplying it by 3 ones, right? All right, any other questions? Yeah.
I just have a small question. I got 26.6 and you got 26.8. Would that be like wrong?
Nah, it's close enough. I don't really care that much about it. When you're doing experiments, yeah, you care about that stuff. But I mean, we're just doing general sort of things here. It doesn't matter that much. Yep. Okay, so any other questions? All right, you can take your break now. So take a 10-minute break. When you come back, we'll do something else, right? The video and go back to the PowerPoint. Okay, so the next thing I want to mention quickly, it's not something I want to harp on, is you got to be a little bit careful with powers of units or converting powers of units. So let's just do this with an example. So suppose, well not suppose, you should know that 1 centimeter is a 100th of a meter. So 1 centimeter is 0.01 meters. And then suppose you have a square that's 1 centimeter by 1 centimeter, and you want to find the area of that square. Well, it's easy to do because the area of a square is just the one squared, right? It's the side times the side, right? So the area would be 1 centimeter by 1 centimeter, which is easy to figure out what that is. It's 1 centimeter squared, right? That's what area is measured in distance squared, like inches squared, meters squared, centimeters squared. So then the question would be, well, what if you wanted to convert 1 centimeter squared or 1 centimeter squared to meters squared? A lot of people think that because 1 centimeter is 0.01 meters, 1 centimeter squared is 0.01 meters squared. But it's not, right? You have to be a little bit careful when you do this. So one way you can figure this out is if you first convert to meters first, and then find the area of the square, it would be 0.01 meters times 0.01 meters, because 1 centimeter is 0.01 meters. But 0.01 meters times 0.01 meters is 0.00001 meters squared. So what I'm trying to say is 1 centimeter squared is not 0.01 meters squared. It's 0.0001 meters squared, right? So you got to be a little bit careful when you're doing units of powers of units, right? Is what I'm trying to say. So the best thing you should do is if you're doing calculations of volumes or areas or multiplying units, you want to convert first before you don't want to do the calculation and convert after. You want to convert first like you did here, right? That's the best way to do it. All right, so that's just a small point. The next thing I want to talk about is something else. The next major topic, I should say, for the PowerPoint. It's the last thing in the PowerPoint, which is this thing called dimensional analysis, which is probably something you haven't done before. So in physics boils down to a bunch of equations that use algebra to solve. You'll see how it works. We'll start talking a little bit about it today, but we'll really talk about it next week. And the point is, you have these algebra equations, and you basically solve them algebraically, and sometimes you get complicated sort of expressions, and one way to kind of see if they're right is doing this thing called dimensional analysis, which I'll show you how it's done in a bit. So let's see what it is. So first of all, the first thing we're going to start talking about is this thing called kinematics, which we'll start a little bit today, but mostly do next week. In kinematics, we deal with distances and displacements or lengths, and we deal with time and things called velocity and acceleration, and eventually we deal with mass. We're not going to worry about mass now. But anyhow, all these things are in equations, and what we want to do is what we call check the dimensions of the equations to see if it's dimensionally consistent. So to do this, you have to know a few things here. So the reason why these things are, we'll figure out next week. But for now, I'm just telling you what they are. So length is given by the variable x. X is really something called distance or displacement, but just think of it as length, right? So whenever you see an x, think of something that has length to it, and that's how it works. And obviously, time has this thing called the dimension of time. It's pretty obvious that time is time. The new thing here is velocity and acceleration, which you maybe have seen before, maybe you haven't seen before. Once again, we'll learn what these things are in detail next week, but for now, I'm just telling you what they are. So velocity is given by the symbol v, and it has dimensions of length per time. It's just something, that's just how it is. Acceleration is given by the symbol a, it is dimensions of length per time squared. And mass, we'll talk about later, don't worry about it right now, but mass is the symbol m, and it's given by dimensions of mass. But each one of these things have this thing called dimension associated with them. And when you put them in an equation, what you can do is check the dimensions of the equation to see if it works out all right. So before we see how that works, which I'll show you in the next slide after this, how it works with an example, and then we'll do an example in the notes. There's a shorthand notation to just notate, I should say, that you're just talking about the dimensions of the variable itself. Not what the variable is, just what its dimensions are. So you put a bracket around the variable, and that just means I don't care what the thing is. All I care about is what its dimensions are. So if you put a bracket around x, the dimensions of x is length, right? So we represent that by an L. If you put a bracket around the t for time, we mean the dimensions of t is time, which we represent by a capital T. The dimensions of t is capital T. And then the dimensions of v are length per time. The dimensions of a are length per time squared. That comes from this, length per time squared. So here it's length per time squared. And then the dimensions of mass is big M for mass. So this is the notation that we use to just work with the dimensions. Okay, so now how do you use all this? All right, so here's a couple examples. We'll do a few more in the notes, step by step. But here's one example. So suppose you solve some equation in physics, and you get this equation. This isn't really an equation. I just made it up, but it could be an equation. So it's 2/3 v times t plus 1/4 a times t squared. And you want to see if your equation is right or wrong. Well, one way to kind of see if it's right or wrong is to check the dimensions. That's the whole point of this. So when you check the dimensions, it's kind of like proportions in the sense that whatever number is there, we don't care about the numbers. So the 2/3 we don't care about. The 1/4 we don't care about. Any numbers you can just disregard. All we're doing is checking the dimensions of the variables, right? So what does it mean to check the dimensions of the variables? It means we check the dimensions of x. We see what the dimensions of x are. Then we see what the dimensions of v times t are, because the first expression here is v times t if you ignore the 2/3, right? So basically what you want to do is check the dimensions of v times t. Then you have another expression here, 1/4 at squared, but you ignore the 1/4, so it's basically 8 times t squared. So then you want to check the dimensions of a times t squared and see what they give you. So then what you do is after you write this out, then you put in the dimensions, so what I wrote here, right? So x is L, so that goes here. V is L over T, so that goes here. T is T. A, L over T squared, so that goes here. And then T, but you got to be careful because it's T squared, so you have to square the dimensions of T. So it's T squared. Then what you want to do is simplify every single expression on both sides, the left and the right-hand side. There's nothing we have to simplify on the left-hand side, it's just L. But everything that isn't simplified, you want to simplify and see what you get. So L divided by T times T is what? It's L, right? That's what I wrote here. What's L divided by T squared times T squared? It's L, because the T squares cancel out, correct? So this thing here, this expression here, this V times T has the dimensions of length. This 8 times T squared also has the dimensions of length, right? So every single thing in both sides of the equation has dimensions of length. They all have the same dimensions when you simplify them. So that means it's dimensionally consistent, which means your equation is most likely right. Now, it could be actually, the number could be wrong. It could be dimensionally consistent but wrong.
Wouldn't that be 2L though equals L, which doesn't make sense?
Wait.
It would be L plus L equals L.
No. So what you're doing is just checking each expression to see if it has dimensions of L. You're not adding it up. It's not L plus L. The first thing has dimensions of L. So this has dimensions of L, right?
Uh-huh.
This has dimensions of L. That's all you're checking. You're not then adding it up,
Okay.
right? You're checking each thing in the equation to see if it has the same dimensions. Okay. Okay, so what I was saying is you could still get the number wrong for x. Does anyone know why you could get the number wrong, even though the equation is dimensionally consistently correct? Because what do we do when you check the dimensions? You ignore the numbers, right? So these numbers are kind of important, right? So if you have the numbers wrong, then your answer is wrong. But if it's dimensionally consistent, it means that only your numbers are wrong. So you just have to check your numbers, not the whole equation, right? That's what that means. Does that make sense? Let's do another one, and we'll do a couple more in the notes. No, so note what this is. It's 2/3 VT plus 1/4 AT squared, right? So then what I'm doing is I'm adding another thing to the end of this one, right? So I already checked the first two expressions, right? It's the same as this, right? 2/3 VT plus 1/4 ET squared. Same thing, but now we're adding this expression here, right? So we want to see if it's dimensionally consistent. So the first two terms have dimensions of L. We already checked that. What about the thing we added? What dimensions does that have? This one, right? So this has dimensions of x times the dimensions of a times the dimensions of t squared, right? Again, right? I'm just following the equation. The dimensions of x is L. The dimensions of a is L over t squared. The dimensions of t is t, but you're squaring it because it's t squared. So what do you get when you simplify this? You get L times L, which is L squared, divided by t squared times t squared, which gives you what? Nothing. It just cancels out, so it gives you L squared. So the point is, one of these things is not like the other, so it's not dimensionally consistent. In other words, if you have 100 terms on the left side and the right side, and one of them is different than all the rest of them, then it's dimensionally inconsistent, right? And what that means is there's no way this equation could be right. No matter what you do, there's no way this equation can be right. So basically what I'm saying is, if you get an equation and the dimensions are all wrong, it means your equation is wrong, right? That's what it means, right? Does that make sense? Okay, so the other thing you can do, and then we'll see an example in the notes. But let me just do one more slide. Is you can use dimensions to come up with dimensions of something new. So for instance, later on, we'll see it in a few weeks, force. But force is defined to be mass times acceleration, something new from the quantities that we already know, mass and acceleration. So if you know the units for mass and acceleration, you can just look at the dimensions for mass and acceleration. You can multiply them together, and that'll give you the units, not the units, but the dimensions for this new thing called force, right? So whenever you see a force, it's a mass mass times the length per time squared. So whenever you see a mass times the length per time squared, it has to be something, has to be a force. There's nothing else it could be. All right, so that's something else you can do with this dimensional analysis thing. All right, let's do some examples in the notes though, right? So we see how it works out. All right, so let me get my notes out. All right, so let's do a couple examples here, or actually a few examples. Okay, so the question is v squared equal a squared, a squared t squared plus, that's still on the plus 1/3 x times a. Okay, so is that dimensionally consistent? It's basically a yes or no answer. Okay, so we need to figure this out. So what we want to do is look at the units of v squared, not the units, dimensions. I keep on saying units. I mean dimensions, right? The dimensions of v squared. So that represents the dimensions of v squared. That's the left-hand side. Really, you can just make a list of each term, but I just do it all in one equation. It doesn't really matter. And then you want to check the units of a squared, right? You got to be careful with the exponents. A squared, and then units of t squared, and then we ignore the 1/3. The 1/3 doesn't matter at all. And then the units of x, and then times the units of a. I keep on saying units. Whenever I say units, just think of dimensions. Times the dimensions of a. Okay, so does anyone know the dimensions of v? Yep. Does anyone know the dimensions of a? Yep. Yeah, you guys are good. Okay. The dimensions of t should be obvious. It's t squared. I mean, dimensions of t is t, but you're squaring it. And then dimensions of x is L. And the dimensions of a again is L over t squared. So now what you want to do...
So x is always length?
Yeah. Right. X is length. So then what you want to do is simplify each one as much as you can and see what you get. So this is L squared over t squared. I'm going to do this step by step. So if I square the L and the t squared, I get L squared over t to the 4th. And then times t squared. And then this one simplifies to L times L. So it's L squared over t squared. What does the middle thing simplify to? So if I multiply L squared divided by t to the 4th times t squared, what does it simplify to? So 2 of these cancel out, right? And you just get, and then you have this, right? Anyhow, the point is every single term in here is the same, right? It's L squared over t squared. Everything on both the left-hand side and the right-hand side is L squared over t squared. I don't know why that happens in this classroom all the time. All right, so so they're all the same, right? They're all the same unit. So is this dimensionally consistent? All the same dimensions. So is it dimensionally consistent? Yes, right? What was that? Sorry? This one? Oh, we can multiply by this L. Right, it's L times L. Any other questions on that one? All right, so let's do another example. This one's pretty straightforward. And it's kind of easy to see how it works out, but nonetheless, we'll do it. So, is t equal 2 times v, so 2v divided by a squared, dimensionally consistent? Because this could be some sort of equation that you figure out somewhere along the way. Okay, so let's figure this out. All right, so what we want to do is look at the units of t on the left-hand side. Units, it keeps on saying units. Dimensions of t. And then the dimensions of v, once again, we're ignoring the 2. And then it's divided by a squared. So it's the units of a squared, dimensions of a squared. So then what you want to do is you want to plug in what these dimensions are. So this is t. What's v again? Right. What's a again? Yep. L over t squared. So this becomes, I'll simplify. You can see it's not going to work out, but let me just simplify it. So this is L over t. And this is L squared over t to the 4th. And then if you divide by a fraction, it's the same thing as multiplying by the inverse, right? Does everyone remember that? So in the end, what you get is L divided by L squared, which is 1 over L. Well, it's t to the 4th divided by t, which is t cubed. And then you have an L in the bottom. So it's not even close, right? It's completely wrong. So there's no way this equation could be right? If you came up with this equation, it's way off, right? So you have to redo everything that you did to get this equation because it doesn't work at all. So this is not right? And there's one more example. I only had 2 examples, but the other class asked for another example, so I made another one up. It's also pretty straightforward because I had to make it up on the fly. And these are things you have to think about. So I had to make it pretty straightforward. So is x cubed divided by t equal to 2v cubed times t squared dimensionally consistent? Okay, so all right. So what we need to do is look at the dimensions on the left-hand side, right? So it's just x cubed divided by t. On the right-hand side, we're going to ignore the 2. So it's the dimensions of v cubed times the dimensions of t squared. So now we got to put in the dimensions of x. So it's L cubed divided by t. One more time, the dimensions of v. And the dimensions of t squared. So this becomes L cubed over t. This is L cubed. The first thing is L cubed over t cubed, and then you multiply by t squared because it's t squared. So on the left-hand side, you have L cubed over t, and what does the right-hand side simplify to? So you have t cubed in the bottom and t squared in the numerator. So what does that simplify to? Right. So they both have the same dimensions, therefore it's dimensionally consistent, right? So that could be a correct equation, right? But the second one we did, there's no way it could be correct. All right, so does that make sense? Okay, so that's how you do these dimensional consistency things. Okay, so what I'm going to do is start the next PowerPoint. The next PowerPoint will not be on the homework tomorrow. It'll be on the homework next week, but I want to start a little bit of it today. So the homework that I'll post tomorrow will just be on what we just finished. It'll be on trig, unit conversions, and dimensional consistency, right? That'll be on the,
So the homework is posted tomorrow and it's due next Friday.
right. Mhm. Okay, but I want to start the next PowerPoint, do a few slides in it. Okay, so this is where the physics starts, right? We haven't done any physics so far. So this is where we're going to start this thing called kinematics one-dimensional, which I'll explain what that is in a minute. But let me go through the first couple slides first. So let me just say what physics is in some sense, some broad sense. You can read this slide on your own later on. But I haven't even mentioned what physics is. We've done math, but basically physics is the study of basically anything. I mean, if you know enough physics, you can do chemistry, you can do engineering, you can do nuclear engineering. There's even biophysics, right? So physics started creeping into biology as well. So physics, is a fairly important science as far as sciences go. So anyway, we'll be learning the basics of physics, right, over this semester. We're not getting that deep into it, just the basics. So let me just say that there are two types of things we'll be doing in physics, basically, and one is sort of like engineering, one is just predicting something. So there's something called a forward problem, which is the easier of the two to do. So basically, if I throw something at some speed at some angle, I can figure out exactly what's going on with that thing. I know how long it's in the air for. I know when it's going to land. I can calculate all those things. Those are forward problems. Those are basically more or less easy to do. So we'll see some examples of that where I give you questions like that. And then there's the inverse problem, which is exactly how it sounds, the inverse of that. So instead of giving you how fast you need to throw something, suppose I want to hit the corner of the room, how fast do I have to throw it to hit the corner of the room, right? That's the inverse of the problem that I'm asking. And that's kind of like engineering. That's what engineers do. Anyway, that's the more complicated case, actually. That's the slightly harder problem. But anyway, we'll see both of those over the course of the semester, and you'll see how they work, right, as we go. I'm going to skip the next slide. You can read that on your own. This is an important slide that most people don't get until maybe too late in the semester. So let me go over it, because it might be obvious, but it's not obvious. I find it's not obvious. So I suspect most of you are biology majors or something related to biology, right? So in biology, you memorize everything, correct? This is the exact opposite way of studying physics. You should not study physics by memorizing things. What you do in physics is you basically should understand how to do the concepts behind the problems and the fundamental parts of the problems well. This is what you want to understand well. And then if you understand that well enough, which takes some people a while to figure out or learn, it's sort of an acquired skill, then you can use that to do any other sort of problem. See, what I find sometimes is people memorize how to do every single step of a homework problem, but they don't understand one single step. All they understand is this step, that step, that step. And that's a gigantic problem, because if I just ask something slightly different on the test, then no one knows how to do it, because you only know how to do that specific problem. And then people get all upset because they spend 10 hours studying for the test, but all they're doing is memorizing homework problems, and they say, I know how to do all the homework problems. Now you know how to memorize all the homework problems. It's different. There's a difference between knowing how to memorize how to do the problems and knowing how to do the homework problems. So anyhow, it will just waste your time if you're trying to memorize everything, right? What you want to do is learn the idea behind each problem, and then get that down as well as you can, and then you can use that to do anything, right? That's the whole point of what we're doing here. So it might be, you might have to retrain how you think a little bit, right, for this course, but hopefully you get it after a while. They don't understand what I'm saying, because it's actually kind of important to understand. All right? Yeah.
Will you upload just the PowerPoint before class so you can take notes on PowerPoint?
Yeah, maybe. Like, I'll upload this tonight, so you have it for next week. We'll do it on Tuesday. Yeah. Okay, so any other questions on that? Because I say this and people still do it. They still memorize things as the semester goes on. Okay, so having said that, now we're going to start doing this thing, talking a little bit about 1D kinematics. Of course, we'll finish it next week. We'll do a lot more 1D kinematics next week. But what is 1D kinematics? So basically, 1D kinematics is basically where every single physics course starts. No matter where you are, MIT, Harvard, here, general physics class here, everyone starts with 1D kinematics. So 1D kinematics is basically the study of how things move. But specifically in 1D, which means in one dimension, which means things are only going back and forth to left and right, basically, right? So it's the easiest kind of physics you can do. Now, typically you don't walk back and forth in a straight line all day. You walk in 2 dimensions or 3 dimensions. That's more complicated. We'll talk about that later, right? We're just getting our feet wet with this 1D kinematics, which is things going back and forth, which you think maybe not that applicable to everyday situations, but it is in some cases. For instance, in a drag race, the 2 cars just go in a straight line, right? Swimming event, they just go in straight lines, right? So even for certain situations, you can use 1D kinematics to study, right? Okay, so 1D kinematics basically, or any kinematics, but we're going to focus on 1D kinematics, but any kinematics requires you to know these 5 things, which is distance, displacement, speed, velocity, and acceleration. So basically what we're going to do is go through these things one by one, and also figure out how they relate to one another. So we're just going to do them in order. We're going to do distance and displacement first, and then we're going to do speed, velocity, and acceleration later. So we're going to just start talking a little bit about what these things called distance and displacement are now. Okay, so there's a lot of text here. Right? I already mentioned this. Read this on your own. Just pay attention to what I'm saying. Right? You can read the PowerPoint later. So, like I said, we're going to start with distance and displacement and see what they are and see what the difference between them is. So the distance, what distance is the total length of the path that you take to get from one point to another point, right? So if I walk around this room, I don't know what the dimensions of this room are. I can guess. So I can go maybe 10 feet that way, I guess. 50 feet that way. 50 feet that way. 50 feet this way, then 10 feet back here, right? So what the total distance that I go is how far? It's 10 plus 50 plus 50 plus 50 plus 10, whatever that is, 170 feet, right? That's the total distance that I travel. That's distance, right? Now, displacement is something different. First of all, it's something completely new that you might not have seen before. It's something called a vector. So a vector is something new in physics that I'll talk about in the next slide. But a vector has 2 things. It has amount and also direction. So this thing called displacement has direction associated with it too. But what I want to talk about now is not the direction, just how much it is. So it has amount or magnitude and a direction. But the amount of displacement is not how far you go. It's the length of the line that connects your starting point to your ending point, right? So if I go all the way around this room and come back to where I started, does anyone know what the displacement would be, the amount of the displacement? 0, because I start and end at the same spot. So the displacement would be 0, but your distance would not be 0. It would be 170 feet or whatever it is, whatever I said it was at first. So that's conceptually what displacement is, right? It's always this, even for 2D, right? But for 1D, we'll focus on 1D. Now, distance is given by the symbol d, which makes sense. Displacement is given by this weird thing, which I'll talk about. It's a delta. So it's a triangle, but it's a Greek letter delta. And delta actually means something in physics. So delta, you get to see a lot of deltas in physics, these triangles in front of things. And deltas mean change, how much things change from one point to another. So this delta x technically means how much your x value changes, right? It's actually defined to be here. It's always defined to be the final point minus the initial point. So you can put delta in front of anything, and it means the final quantity minus the initial quantity. So this technically means the final x value minus the initial x value. But you don't need to think of it like that. We seldom actually ever calculate the delta x in 1D. All we do is think, how far do we end up from where we start? And that's the amount of delta x. That's what delta x is, right? That's the displacement, right? But it's actually sort of an equation buried in there. All right, so does everyone more or less understand that now? I mean, we'll get into the details later, but does everyone get the general idea? Now, let me say something about vectors and scalars before we go on. So, like I said, the displacement delta x is this new thing called a vector, which has not only a magnitude, but also a direction, amount, but a direction. So a typical sort of example of the difference between a scalar. Scalar, by the way, I didn't mention a scalar. Scalar is just a normal quantity, right? It's things you've been using your whole life. They're called scalars, but the things with a direction are called vectors. So anyhow, the difference between a scalar and a vector, the obvious one is speed and velocity, which is another vector, which we'll talk about next week. So if you're going in your car, if you're on 95 and you're going, I don't know, it doesn't matter, 70 miles an hour, that's your speed. That's how fast you're going. If you're going towards West Palm and you're going 70 miles per hour north, that's a vector because you're saying how fast you're going, which is your magnitude, 70 miles per hour, and you're also saying what direction you're going, right? So the fact that you're giving two things, how fast you're going and the direction that you're going, is something else called a vector, which is velocity, right? So they're two different things, right? So that's what a vector is. Now, when you distinguish vectors from things that aren't vectors, typically when you type them out, you type them as a boldface thing. If you're writing them out, if you're writing them on paper, it's pretty hard to write in boldface. I mean, you can try it, but I don't think anyone ever writes in boldface. So you draw an arrow over the vector, over the thing that's a vector, and that represents that tells you that thing's a vector. Also, what you can do is talk about the magnitude of a vector. So in other words, a vector has a amount or a magnitude, amount and magnitude are the same thing, and a direction. For instance, 70 miles per hour north is the vector. But if you just want to focus on just the magnitude, 70 miles per hour, you put that thing in, you put the vector in absolute value, and that just means you're just talking about the amount of it, and you don't care about the direction. All right, so does that make sense, what a vector and scalar is, the difference between them? All right, so the fortunate thing is we're not going to get it too into the technical definition of how you actually write vectors. So there's a formal way of writing vectors, and we're not going to do that for 1D vectors. So what we're doing is technically not 100% correct, but the point is, this is the first physics you see. So for me, you don't want to get that technical about how you write things and then worry about all the other stuff. We'll worry about all the other stuff later. When we do 2D vectors, we'll do it the proper way. But for 1D vectors, we're going to fudge it a little bit and do it a little bit easier than it should be done. Yeah?
I had a question on 2D vector. Would a 2D vector be a vector moving in every direction?
No, 2D vector is just, it's hard to explain now. But when we get there, it'll be obvious what a 2D vector is. I mean, I can get into all the technicalities, but it's going to be confusing, and you'll see it in a few weeks, and it makes more sense. So when you talk about 1D vector, right? So basically, if you think about something moving in 1D, say in the x-axis, right? You can either go left or you can go right. There's only two ways you can go. So basically, if you go left, you're going in the negative direction, correct? So if you write your delta x as a negative number, it means that you're going in the negative x direction. It implicitly tells you the direction, right? If I say delta x is minus 5 meters, I mean I move 5 meters to the left from where I started, right? If I say delta x is plus 10 meters, I mean it means I'm moving 10 meters to the right of where I started. So that's how we're writing vectors. We're just writing them as plus or minus. We're not getting fancy writing them as vectors with an arrow over them. We're just saying delta x is minus 5, delta x is minus 10, delta x is plus 10, delta x is plus 15, and things like that, right? That's how we're going to start. Now, if you write delta x is like that, if you write delta x is minus 5 meters, the minus 5 means you're going 5 meters to the left, right? So what I'm saying is delta x can be negative or positive because it indicates the direction. However, if you're talking about just the amount or the magnitude of a vector, like the displacement, it's always a positive number. So the displacements can be negative because they indicate direction. But the magnitude of the displacement, or any vector, doesn't matter, it's not just displacement, the magnitude of any vector is always positive, right? So I can say delta x is minus 5 meters, meaning I move 5 meters to the left. But the amount that I moved is what? It's 5 meters. It's not negative 5 meters, right? I moved 5 meters to the left. So that's an important thing to understand, that magnitudes of vectors are always positive numbers, even though the vectors themselves can be negative. All right, this is as far as I got in the other class. So I like to keep the classes lined up with one another. All right, so you guys can go, and I'll see you on Tuesday.